All right, Bismillah Rahman Rahim. Um, I want to finish our discussion of camera geometry and single view and multi view geometry today, and there's just a little bit part which I wanted to show you, which is this very interesting technique of structure for motion from a lot of unordered photographs. So the plan for today is that I will just go through this quickly, and then we'll be done with this module, and in fact we'll be done with the first half of the course, which deals with geometry, camera geometry, and then we will start with the semantic understanding of images, which is content of the image itself rather than the geometry. Okay, so so let me talk about it. This is a very interesting paper and very interesting technique which works very well in practice. It's by the group in University of Washington at Seattle. So we looked at SFM, structure for motion, for the case where we have a video. And video has some ordering in it, right? There is one frame and the next frame and the next frame. So the frames are taken from close proximity. There is some rotation and translation of the camera, but it's all like one content. Okay. But this is a very different formulation of SFM. There are images available on the internet. So if, for example, if you look up LUMS campus, you'll get a lot of photographs of LUMS campus. Now these photographs collectively show a lot of different views of the LUMS campus, but the problem is different from video. In video, one thing, the camera was the same. The camera intrinsics were the same, only the extrinsics were changing. And the extrinsics from one frame to the other frame were also changing smoothly, slightly, right? Because the video is a high frame rate process. But if you look at photographs of LUMS campus, they will be taken from different cameras, different times of the day, different viewpoints, the different lighting conditions, and so on. Okay, but indeed they are views of the same environment. Okay, it's just that if I put them in a list, the first one will be from here and the second one will be on here. They will be like from random locations and so on, but they are views of the same environment. So the question one can ask is it possible to take all those views? And I know nothing about those cameras. They are non-calibrated. I know nothing about how to what's the order in which the photographs were taken, but can I reconstruct structure from that set of multiple images? Okay, so this is the problem that these guys looked at. This is work by Steve Seitz and Noah Snavely at University of Washington in Seattle. Very interesting work, and it works very well in practice. The code is available. You could actually try this out. Okay, so what they did was here, for example, they look up this Trevi fountain in Rome. They look at that, they search Flickr. They got a lot of images of that fountain, and from those images of different tourists who went there to photograph that fountain, they reconstructed this point cloud. So what you see here is the reconstructed point cloud, as well as the camera location of each of the photographs, right? So it's pretty impressive because we did not know who took this photograph, when the photograph was taken, and from where the photograph was taken. But remember, like we did in rigid structure for motion Tomasi and Canary method, the solution, when you find the solution, you find information about the camera as well as the structure, because those two variables are tied. Okay, so I just want to very quickly give you kind of an overview of this method, not the full details of it that you can look up later. So this method is also called bundle adjustment because of the type of optimization algorithm that has been used. So there is one camera which is taken a view of an object. There's another camera. These are diverse cameras. They don't have anything in common in terms of their parameters. Then there is another view. So there are a bunch of views of an object that you have, right? You have a question? Oh, okay. So there are a bunch of different views of the object. All right. Then what you have what you can do is, which is actually a critical part of the algorithm, is that you can find some corresponding points between those views. Now this part is harder than this part of finding correspondences between the images is harder for this problem than for the video problem. Okay, because in the video problem, if I find a point in the next image, because the camera has moved a little bit, rotated a little bit, that point should be somewhere close by. I do expect to find it. Okay, but these photographs are completely unordered. I mean, when I download these images, I don't even know they are photographs of the same place. Okay, I'm just using a tag, so I'll have to find which photograph is similar to which photograph, and where do I expect to find common points. Okay, but there is a very robust algorithm to do that, to find point matches between different images, and so they used it. That's we'll go through that work inshallah in the next module, which is called the SIFT corner detector. Okay, so let's just assume for now that there is some way to find matches, that which photograph, you have like 1,000 images, which one should match to which one. Maybe image number 1, 23, and 99 should match. Okay, or so you actually form clusters between images and try to see which ones are giving you good matches between based on how many points match between those images. Okay, so that's a non-trivial step. It's not that it's like simple, but there are good algorithms to do that, and so one can just use that. Okay, and once you have that, so that forms your input to the structure problem. And then they did not take any simplifying assumption that the camera should be orthographic, which is a limiting assumption. So they did not do that. They took the full perspective camera. So what are the unknowns here in this problem? The unknowns are these world points P, right? And also the R1, T1, R2, T2, R3, T3, the extrinsic parameters of the camera. Not only that, actually, the intrinsic parameters of the camera are also, I mean, all the camera parameters are unknown right now, because that information may or may not be available. Now, sometimes the information about the camera intrinsics is available, because a lot of cameras, when they take an image, they save the camera name, the focal length, the type of sensor. They save a bunch of what was your ISO setting, for example, or how much exposure setting did you have. They save a bunch of that information into what is called the EXIF data. So that EXIF data is written into the JPEG image file or the TIFF image file that the camera is creating. Okay, a lot of modern cameras do that. Not every camera does that, and it's actually a setting that sometimes you can turn off. But a lot of images available on Flickr will have EXIF data with them. Okay, so if EXIF data is available in a problem like this, you can assume that the camera intrinsics are known, because you can extract the K matrix from that EXIF data potentially. Okay, they just give you the camera name, but there are other websites where you can go and look up the camera name and find out what was the size of the CCD array for that camera, and so on. And then the focal length parameter is also available in the EXIF data. But the camera extrinsics are not recorded anywhere. Okay, sometimes you might have a GPS tag with an image, so you roughly know where the camera was in the world, but that's about it, and that's not extremely useful in a problem like this. Okay, so that's the problem. I mean, those are the unknowns. But if I find those, yes, go ahead. Yeah, sometimes they do. Yeah, I'm not sure what they exactly did in this paper, but yes, one can download only those images that have EXIF available. That's possible. That's a valid formulation of the problem. Okay. Now, now, okay. So those are your unknowns. But what is your constraint? The constraint is that if you are able to find the correct P's and the correct R1s, T1s, R2, T2, R3, T3, then you project that P into your image, and it should overlap with the marked image point. Okay, So that can give you a cost function, a kind of like a function to optimize over, right? That is my R1 T1 R2 T2 R3 T3 and the set of P that I estimated now, is that correct or not? If it projects well onto your image data, then it's correct. If not, then you can further search for a better solution. So that's the idea. It's an optimization problem. And in fact, because they are not using orthographic camera model here, this is actually a non-linear optimization problem. Where is the non-linearity coming from? It's coming from the camera model. The camera model itself for the perspective camera is a non-linear model. Okay. So it turns out that this is an optimization problem. In general, I'm just writing it as you have to optimize some function g of r, t, and p. Okay, and that function g is actually easy to figure out. It's just that if you, I mean, what is a cost function supposed to do in an optimization? The cost function is supposed to tell you, if you give me a solution, I'll tell you how good that solution is. Okay, so that's actually easy to write here. The cost function should be, okay, you give me an RT and P, I will project those P's according to R and T, according to the camera model, and see how close they are to the image points P. If they are very close, you have a good solution. If they are not close, you have a bad solution. Okay, so you set up a cost function like this, and then you optimize over that cost function, which is done through gradient descent methods and so on. There are many optimization techniques that one can do. The particular technique that they used here is called, it's a nonlinear technique. It's called Levenberg-Marguerite optimization. Yeah. It doesn't have to be. In fact, it's not convex. If it was convex function, then optimization converges very well. If it's not convex, you have the chance of getting stuck into local minimas and so on, and that's all part of the equation here. It could, and then there are checks in the technique to try to ensure that you don't get stuck in a local minimum. Okay, so essentially they're using Levenberg-Marguerite optimization routine, but the way they pick their data is also very interesting. There are lots of details here. They don't, if you're given a lot of images, they don't take all those images together. They first find the strongest match between the 3 or 4 images, and then they keep adding more images to see if they can grow that match and so on. And that actually helps in the stability of the think of it like this, that you have good ways to get initial guesses. Okay, yeah. How is the perspective camera model? Because there's a division involved there, so that's the reason the perspective camera model is nonlinear. Fx over z. Okay, so essentially it's nonlinear. We wrote it as a linear model in the P2, P3, P2 space, but ultimately, if you want to relate it to image points, it's a nonlinear relationship, and so you need a nonlinear optimizer like Levenberg-Marguerite or some technique like that. Okay. All right. So the objective function is really this, that now this notation is slightly different from the notation I've been using, but it's almost the same because I've taken these slides from Steve Seitz lectures. So this x here is a world point. Okay. So Rx plus T, that's the rigid transformation of the world point, and then you have the camera model, which is the nonlinear model. So really you have a P matrix. To get the image points, you have a perspective matrix, which is a function of R and T, and then you multiply the world point with it, right? So that's the function which gives you image points. It's the same model that we have done. There's really nothing different here. It's just written in a slightly different way. And then you minimize over the world points, the rotation, and the translation matrices. And how do you minimize that? Well, you first project that known world point that you think of, you project that into the image space. That's the projection, which is the predicted location of that world point, and you subtract that from the actual image point that you have. If they are the same, then this error will be 0 or it will be low if they are close. If they are not close, that error will be large, and so you can just take the norm of this over the whole sum. And there's a weight function here that has to do with how the images are sequenced in their algorithm. So I won't go into that detail, but really it's a reprojection error minimization. Okay, you will see what reprojection error is in your homework. You have to, when you are estimating the camera calibration matrix in this homework, you have to look at the reprojection error, which is really the world points projected onto the image, subtract distance of that from the image points themselves. Sorry? Yeah, I'm just saying that this is really the camera model, right? The world points and the camera matrices, the camera parameters, there's some function of that which you understand what that function is to give you the image points. Okay, these are the projected image points into the world. So the cost function is really the projected image points minus the actual image points, the sum of squares of that. Okay, now this is a nonlinear cost function because there is a nonlinearity involved in the camera projection, and so they minimize this. They have some method to minimize this, which are nonlinear optimizers. In this case, the algorithm they use is Levenberg-Markadit optimization. That's just a nonlinear search method. It's an iterative method. They start from some place and they converge to a solution. Okay, so it's just basically a huge minimization problem where I'm trying to simultaneously estimate the world points, the camera locations together, the camera translations and rotations all together. Okay. Okay, so it turns out that minimizing this cost function g is difficult. It's not a straightforward minimization because g is nonlinear due to rotations, the perspective division. There are lots of parameters. There are 3 for each 3D point. There are 6 for each camera, 3 coming from the rotation, 3 coming from the translation. I think they're assuming that the camera intrinsic parameters are known from the EXIF data. It's also difficult to initialize this. What's a good initial guess for these points? You don't know. And there is this thing called gauge ambiguity. The error is invariant to a similarity transform. So, if you have translation, rotation, and uniform scale, there are configurations of cameras which will yield you the same error function. So there are many techniques to use for nonlinear least square optimization. And the technique they use here is based on Levenberg-Markadit, but the particular technique they use here is called bundle adjustment. What they do is they do this problem iteratively. They're given a lot of images. They don't solve all of them together. They first find the best few matches. Then they grow that match and grow that match and grow that match. And in the sense, the best few matches gives them the strongest initial guess, and then that keeps improving as you add more images into that bundle. There is a code online available. You can actually download it, try it. We tried it here, for example, for the SSE building. We took a bunch of photographs of the SSE building and it constructed a very realistic 3D point cloud of that building. Okay? Yeah. Okay, the question is, if I know the intrinsics from the EXIF data, can I do just find the back projected ray? Well, you can only do that in the canonical viewpoint. And so here you have a bunch of cameras, so all of them cannot be assumed to be in the canonical viewpoint. Then your world points will all be in different coordinate frames. And if you want to do it in the non-canonical viewpoint, you do need the R and T parameters. Okay, so I'm not going into the detail of the method. I just want to wrap this up quickly. But their results are really amazing and stunning, really, because it's a very difficult problem to solve. So what they did was on Flickr, they searched for images of Rome. Okay, this is a paper titled Building Rome in a Day, because they had about 24 hours of computation to build the 3D point cloud that they needed. So what they do is they search for Rome on Flickr, and Rome is a popular tourist destination, so a lot of people take photographs when they visit Rome, and then they upload those photographs on Flickr. So Flickr has an API. You can download those images, and you can get their EXIF data and so on. So they use that. So they searched for Rome. They got like about 1.2 million images of Rome. Okay. Now remember, you don't know anything about these images. They could be inside, outside. They could be personal photographs. They could be photographs of the architecture. So really, the input data is very diverse and real. It's not like engineered to fit my problem or anything. They're just downloading images from the web, right? Um, so here they're showing you 50 images from the data set they downloaded. And now, yeah, yes, exactly. Yeah, that's a very good question. So that's actually built into the technique. I mean, you get a lot of images, like you see in this photograph. I mean, there are these two ladies standing here. They could be anywhere in the world, right? It's there is no Rome in this picture. I can't see, or I mean, this photograph here, this one. I mean, there are a bunch of like really random photographs here. I mean, this red car here could have been anywhere in the world, right? Uh, and even if it is in Rome, it's not giving you any information about Rome. It's just a close-up view of a scene. So it's not easy to automatically, and they were not doing any manual processing here. Somebody's sitting there and marking this is a good image and that's not good image. That's not the idea. They want this to happen completely automatically. So the input is just the downloaded data set of Rome from Flickr. Now, what they do is actually, I've not gone through the technique, but actually the technique works like this. What I do is, in a nutshell, I'm describing the gist of the idea, right? What you do is you have some matching technique where you can say that this point in this image looks pretty awfully similar to this point in this image, okay? Or given two images, you have an algorithm that says, okay, these points should match to these points, okay? And we'll do such algorithms in the next module that we are starting in a moment, okay? So what they did was they said, okay, if I have 1,000 images, let me compute the matches of all those thousands with each other. That's 1,000 square image matching, pairwise image matching computations. They exactly didn't do that. They have some pre-filters to say this cannot be matched to this at all because they are completely drastically different based on some tests, so that they reduce time. But essentially think about that I could do these n square matches, okay? Then from that I can find the pair which has the strongest match, okay? Now that could be a photograph of Rome, it could be a random photograph, okay? Now I got this pair, I find the next strongest match that can match to this pair, okay? Now if I do that a bunch of times, what will happen is that those things which people photograph a lot more will start to appear, right? Because these random photographs of, let's say, these people here randomly, there won't be a lot of images exactly like this which are matching to this one. But if you look at, for example, Colosseum, so there should be a lot of images like that because that's a landmark. So when I start building the Colosseum images and start matching them, I'll get like a big cluster. And so in a sense, through this matching process, there is a natural filter in there which will discard the unimportant things because they don't seem to have a lot of matching images. And it will tell you, well, this is a really important site because I found out of these 50 images, maybe I found like 10 which were of this site. Except they didn't do it for 50 images, they did it for 1,000,000 images, right? Okay. So if you look at this, if you look at these 50 random images, there are some important images in this, like this site, which is, I think, the Triviri Fountain. It's like an important image which will appear many times because a lot of tourists go and take this photograph. Okay. Or this one, like the Colosseum image. I mean, a lot of tourists would take a similar photograph. Yes, the person's hair will be different because they are different people, but in the background you have this building of the Colosseum, and there will be a lot of images of this. Okay, because that's just a naturally attractive place in the scene. Okay, or like this image, or like this image. I mean, these are all important places in Rome. Yeah. Because there's a matching. I mean, they could be Rome, they could not be Rome. It doesn't really care. It just looks for clusters of matches, right? Now, since I wrote Rome in the search, and I downloaded all images which were tagged by Rome in Flickr, if I find large clusters in that data set, which were like in the million images, I found a cluster of like, let's say, 2,000 images, which were all the same. I mean, they matched with each other very strongly. And I downloaded them with the tag of Rome. Most likely, that's going to be a location in Rome. Yeah, so I'll find a bunch of clusters. Yeah, any set of large clusters, I'll use them. Okay, because they have matching points between them. So this process really depends on the strength of the matching algorithm. And so those matching algorithms are not trivial. In fact, a lot of problems in vision require a matching algorithm to begin with. You were estimating homography. If you want to do that between two images, you would need some sort of matching algorithm to say this point is the same as that point. We want to find the fundamental matrix. We have to have some matching algorithm to begin with, saying these points are the same so that I can estimate for the fundamental matrix. You want to do camera calibration, you want to do this sort of structure for motion. A lot of things in vision actually uh, depend on the matching algorithm, the point matching algorithm. So that's actually a very crucial component. When you are building a product, the client doesn't see it. I mean, think about the product in your camera, in your phone, which is the panorama building product. I mean, at the crux of it is, the crucial component of it is the matching algorithm. If the matching algorithm was not good, your panorama will not turn out to be good. Now, as a consumer, you don't see that. You say, oh, it's a nice product. I move my camera around, I get a panorama. But essentially, underneath is the matching algorithm. So it's actually a very crucial component of the of a lot of vision algorithms. Okay. All right, but these are just 50 images of Rome. Now I have 200 images here, random 200 images from the dataset we downloaded. Okay, so notice that this image again is one of the like famous places in Rome. It's an archway and entrance. Okay, and here I have 800 images, and now notice that this image and this image and this image are really the same location, right? But they are different tourists photographing the same location, and that's really what gives me structure for motion here. I can find out automatically that these images cluster together, okay, because they have strong matches between them. They have a lot of matching points between them. Okay, yeah. We'll come to this. You'll get a homework on them. Yeah. Yeah. Yeah, I mean, Facebook face recognition is a different category of matching algorithms. They actually understand that this portion of the image is a face. That's the first part, which is a face detector. And then they understand that this face matches to some of the previous faces that I've seen in the same guy's timeline or stream, right? So we will go through these algorithms or the nature of these algorithms later in the course. That's what our second module of the course is all about. The second half of the course is all about. Okay, so now you can download more images. This is 20,000 images of Rome, and then these are 1 million images of Rome. Okay. Okay, so that's your data set. It's a big data problem, right? You're gonna, I mean, it's a pretty challenging problem. You want to make sense out of these 1 million images. In fact, you want to extract structure, the 3D structure of different places in Rome, and you don't even know what are the places in Rome, right? But you want to extract that automatically out of these 3 million images. It's a phenomenally challenging problem. So what do you do with this? So this is what they did in this paper. They took about roughly 1 million images, and they had about 1,000 cores of processing power available with them. And then in one day, about 23 hours, just under 24 hours of computation time, they were able to reconstruct some important buildings, important tourist sites in Rome. Okay, these are the sort of clusters they got on a map, right? Every line, every red dot is an image location where the image was shot from, and every line is between two image locations is that these two images matched with each other. Okay, so now you see that on a map they kind of cluster together, and that's because there are some important sites in the city that get photographed very frequently. Okay, so that's St. Peter's, there's Colosseum, there's Trevi Fountain, there is Forum. These are all the famous landmarks of Rome. Okay, so these were automatically extracted. These clusters were automatically extracted out of those unordered million images. Okay. So this is to give you an idea of the reconstruction. So this is reconstruction of the Colosseum. You see each of the pyramids, black pyramids that you see is a camera location. So the tourists descend all around the Colosseum and take a lot of photographs. That's what tourists do, right? They just go around and take photographs. So all of those cameras have been reconstructed for the images that came in the Colosseum structure cluster. Okay. And the point cloud is the point cloud of, so this is a 3D point cloud. This is the point cloud of the 3D structure itself. Okay. So this is St. Peter's Basilica. It's a building. Not only have it been constructed from the outside, it has also been reconstructed from the inside, because there were a lot of tourist photographs from the inside also. Okay. Yeah. That's a byproduct of the optimization process, right? The optimization happens over the world points X, the camera rotation R, and the camera location T, the translation T, right? So once the optimization converges, you have the correct world points and you have the correct R and T for each camera. So you can show that R and T as one of these black pyramids that you see here, right? Each one of them is a different R and T because it's a location in the world and a translation. Okay. Now remember how many unknowns here in this problem. You have the number of points in this point cloud, which would be like several thousands or million maybe. You have the 3 times, you have 6 times the number of cameras, the number of images really. So it's a huge problem, a huge optimization problem to solve. Okay, yeah. No, no. In general, for highly nonlinear functions, which this is, in general for highly nonlinear functions, the guarantee that you will reach a global minimum is not there because you are searching in a very high dimensional space. I mean, the dimension of this unknown vector is running into hundreds of thousands, right? And so the guarantee that you will converge to a global minimum is not there. But you build in a stable algorithm, you built in some checks so that if you get stuck in a local minimum, you are able to recover from that reasonably. So you just run this you keep running this optimization till you feel that your error is good enough. Well, but you keep checking the reprojection error, because every iteration gives you a reprojection error, and when the reprojection error is good enough, you stop. What? Yeah, so they ran this. So they ran this optimization for about 23 hours, and then this is the result they got. Now, there is, it's a good enough result. It looks visually pleasing, but there could be better solutions where some of these points are at more accurate locations. But that's like they are saying, okay, good enough. I've converged. That's what you typically do in highly nonlinear problems. The guarantee that you have reached a global minimum can be achieved only for those problems. Well, for linear problems, you can achieve that. For nonlinear problems, if the cost function is convex, you can still give guarantees on on the uh, on the optimization. But if the cost function is not convex, then there aren't strong guarantees that you will converge. Okay, and so you have to do a lot of experimentation and trial and build your techniques so that you don't get, even with bad initializations, you're able to converge. And often you show that through examples that, look, I took a lot of examples and it still works, so it's kind of like a good algorithm. These optimization algorithms, this is a whole course, right? The introduction to optimization algorithms, and people interested in vision, they should take that course, because a lot of computer vision is just optimization. G, you have a question? या आप अभी आए हैं और आपने पूरी क्लास में हलचल मचा दी, राइट? अगर आप लेट आए हैं तो be a bit apologetic about that. Don't disturb the people जो पहले से बैठे. Okay. So I'll show you one more example. This is a pretty impressive example because they took a small town, which is an old historic town, and it has a lot of alleyways and narrow streets and so on. And so it's not like all the tourists were taking photographs of like one central object. They were just wandering around this town and taking photographs. And so the matching problem is even more difficult. But the reconstruction of point clouds is pretty impressive. So the entire kind of village is reconstructed. And you see from the camera locations, these black pyramids, you can see that they are spread out all over the town. Okay? Yeah. No, this whole town is a tourist site. It's a historic village. So there are people walking in the streets, and they took pictures from all over, right? So it's like one contiguous cluster of photographs which match with each other in that cluster, and the mountains behind it and so on, because they appear in those photographs. Yeah. Yeah, here we are talking about like a million images. Yes. No, you don't make sure. Like I said, you actually just you do a Google search or a Flickr search, right? So you write the name of this town. Now you get a bunch of images. You don't know whether they're all from this town or not. But the matching process picks up the strong clusters. And so there would be a lot of photographs that are not relevant, like I showed you in the Rome case. There are a lot of photographs which are not relevant. In the clustering process, they themselves get dropped, because an irrelevant photograph will not match to a lot of other photographs. But a relevant one, like the tower here in this town, a lot of people photographed it. So that will form a large cluster. So I only take large clusters. Yeah. Famous places. Yeah, yeah, exactly. But there will be a lot of personal photographs of Paris when you download that, which will be close-ups of people, and they will just get automatically dropped out. Okay, so So there's some. This is a extremely good website for this method. This is work, like I said, by Steve Seitz and Noah Snavely in University of Washington at Seattle. You can look at this. The paper has a lot of citations. They had a catchy title to this paper, "Building Rome in a Day," because they had like 1 day of computation, 24 hours of computation to build these videos that I showed you. Yeah. Yes. Okay, so the question is that this will naturally pick the famous sites in the city because the non-famous sites don't get photographed a lot, so they're not in my data set. Yeah, that's true. Now, if the objective is actually to construct a full 3D model of the city, there are many methods to do that, and people have done that. So you see, for example, a lot of cities in US, you go to Google Maps, you see 3D building structures in those cities, right? Now, how is that done? There are a bunch of different data sources which are used. So you have satellite data, which is also doing stereo mapping. So you have some satellite data which is taking multiple images of the site, and you can use that. You have aerial surveys. So people do low altitude aerial flights over the city and take stereo pairs of the whole city in a survey pattern. But then there is also Street View, and Apple and Google both have used Street View type of imagery to actually do a lot of 3D reconstructions also. So there are many different ways possible to do those three. Sorry. Yes, yes. But there are many different formulations of this problem, and people have done it in a whole different ways. So the Street View cars which drive, Google has those, right? So they take a lot of views of the same scene because the camera is taking a lot of images, and even that can be used to actually construct 3D models or to take existing block level models that were created by the satellite and texture map them so they look like an habitable environment. Okay. So the 3D structure reconstruction now is quite a mature, at least for rigid structures. It's quite a mature, stable field. You can get really working algorithms. Apple's iPhone X is an example. It actually constructs the 3D of your face when you take a selfie, um, and um, there are companies, for example, that use. I know a company in Saudi Arabia. It's a startup. They use drones to do, for example, site surveys for civil engineering sites. Okay, so how would you normally do a survey? You need to do this theodolite on a tripod and put like a laser, and you put a measuring ruler and see where that laser hits, and you do site surveys like that. What these guys do is they just fly a drone over a site in a zigzag pattern, do this image matching, and construct like beautiful 3D measurements of the site. Okay. Yeah, I mean, there is a problem that you are viewing from the top. So what about this side face? Will you be able to reconstruct structure for that? So they have a whole algorithm to plan the path of the drone so that they get good coverage. Okay, yeah.
So if you have an object and we take the pictures from arbitrary cameras, arbitrary position cameras, and so the same object which for which we take pictures for two cameras that have very unique translation and location between them. So none of the 3D structure बनाने से
The question really, the way I would put it in vision terms is, how does the baseline between the cameras in a stereo case impact the quality of reconstruction? So this is actually a paradox. It's kind of like a fundamental problem with stereo in some sense. Well, it's not a problem, it's just an observation. The accuracy of reconstruction generally should increase as the baseline increases, right? Because you have more varying viewpoints, so you have a higher kind of difference between the two images, so you can lock better your unknown parameters. But if the difference between the images is too large, the matching problem that you need to actually do the reconstruction becomes more difficult. Okay, so generally this is called wide baseline stereo. Generally, wide baseline stereo is recommended. If you can do this matching problem, then the accuracy would be better than narrow baseline stereo. In narrow baseline stereo, because the viewpoints are close to each other, the matching is really simple, because this image approximately looks like this image. So the matching is really simple, but then the accuracy of reconstruction won't be that high.
So इसमें आपको देखा होगा जो होता है
Yeah, I showed you results of that. All right, so this completes half of the course. We are done with geometry. Okay, and we were supposed to complete that yesterday, because yesterday was the halfway lecture, 14 lecture, because there are total 28. Okay, but yeah, we are almost on target, right? And so I'm gonna start with the next module, which is feature detection and matching, and we will build towards, using this feature discussions, we will build towards machine learning, which are the next module. How do you learn stuff on image contents? Okay, so this is a complete shift of gears, because so far we were talking about the camera geometry and the rays that you cast in the world, and how do you back project and how do you project and so on. We are done with all of that, right? Now we are gonna all of that was, we talked about the geometry of the camera or cameras. We did not talk about the actual pixel value. We just talked about pixel location, because pixel location is a function of geometry, but we did not talk about what is the image about. Is it a face? Is it a dog? Is it a building? I mean, we never did any discussion on the color values in the image. Okay, because we were purely discussing the geometric relationships of camera. Okay, so now we are going to completely shift gears. It could have been a separate course. I mean, I just put the two things together in one course. We are now going to completely shift gears, and we are still going to start talk about the content in the image rather than its geometry. Okay, so it's a different treatment now. Okay, so that's why in the beginning of the course I showed you this slide when in the introductory lecture I was saying this course has two themes. There is camera geometry and there is object recognition. And now we are done with camera geometry. And we'll start talk about, so camera geometry is camera as a measurement device. And then object recognition, camera as a device to extract semantic information from images. Okay. All right. So the first topic that I'll deal in this is edge detection, which is a simple type of information to extract from images. Okay, that's where I'll start from, and then we'll slowly build about corner detectors and more complicated features to match between images. Okay, that's feature matching is the first module that we are doing here. Okay, so what is edge detection? The goal of edge detection is to identify sudden changes or discontinuities in an image. Okay, intuitively, most semantic and shape information in the image can be encoded from edges. If you look at this image, I mean, this is a drawing, it's not really a image from a camera. But if you look at this image, you do not have any texture information, you do not have any color, you do not have any other form of variation between the pixels. In fact, you don't even have any gray levels. This is really a black and white image. There are only two colors in it. So this image is really stripped of all the different richness that an image can have, like lighting and shading and color and so on. All of that has been removed, texture and so on. All of that has been removed, right? But you still, even with this minimal information that has been left, which is only the edges of objects, you still have no difficulty in interpreting what this image is. Okay, yeah, you know it's a room, there's a bed, there's perspective, you know where the camera is relative to the objects. You can infer all of that from this image. Okay, you can infer the vanishing points, where would the horizon line be. You can compute all of that from this image. Okay, so intuitively, most semantic and shape information from the image can be encoded in the edges. Okay, and they are more compact than pixel representation. So this is an ideal edge detection. This is an artist's line drawing, but the artist is also using object level knowledge here to create this line drawing. Okay, so that's kind of like motivation to look at edge detection, because we feel that in human perception, edges only can give you a lot of information about the scene structure or the scene content, really. semantic understanding of the scene. Yeah. Uh, I mean, if I take the pixel dimension of this image, right? I mean, this could be 1,000 by 1,000 pixel image. So there are like a million pixels in this, and if I store that, I'm storing the color value of each of those million pixels. But now, if I want to store these lines, that's actually a lot more compact information, because I could just store the endpoints, the two endpoints of each line. So there's a bunch of white space here that I don't really need to store, which if I have a pixel image, I will need to store that. Okay. All right. So why do we care about edges as motivation to study edge detection? We have to extract information and recognize objects. That's our ultimate goal. We want to understand the image content, and our observation here is that these edges actually contain a lot of information about image content. Maybe I can do something with these edges to try to understand image content. Okay, so that's motivation number one. And motivation number two is also that edges help me understand geometry. Remember, a picture has vanishing points and vanishing lines, and those vanishing points and lines actually are a function of where the camera is and where the geometry is. So even for the understanding of geometry, we studied geometry, we just assumed that this is the line that I found in the image, but there will be some edge that will correspond to that line. So if I want to do that automatically, if I want to extract that geometric relationships automatically, for example, I have a self-driving car, and the car has a camera mounted in it, and I want to find out where the horizon line is and how much is the tilt of the camera with respect to the horizon line, with respect to the ground plane. I can do that by detecting edges first, and from that edges I can find the vanishing points and join the vanishing points to find the vanishing line, and then the vanishing line coupled with the camera K actually gives me the tilt of the camera. It can give me the ground plane normal, so it gives me the tilt of the camera. That's part of your homework. You have to do that in the current homework that's due on Tuesday. Okay. All right. Here's an example. This is from our own work. Actually, the guy who did this work, the PhD student who did this, is graduating tomorrow. In the convocation. We made a new method which uses angles between line pairs, just the information in angles between line pairs to extract 3D structure. And there are a bunch of steps of this algorithm. But the first step is that we detect lines. And then from those lines, we find line pairs and plane orientation hypothesis, and then we form rectangles out of this. We do a whole lot of stuff to actually get to the 3D structure of the building. Okay. So that's motivation to talk about edges. Why do edges arise in an image? Edges actually arise because of a variety of factors. First is surface normal discontinuity. So what's happening is that there are surface normals here on this round part which are changing. But then after this occlusion, the next pixel has a surface normal which is a wall, so it's going this way. So there's a discontinuity in the smoothness of the surface normals, and that generates an edge. There's a depth discontinuity here because this object and the object behind it is at a depth. There is a color discontinuity. The surface normals are continuous here, the depth is continuous here, but the color is different, and that generates an edge. And there's an illumination discontinuity. Here's a shadow. Surface normal is same, depth is same, but this shadow generates a color change, and that actually gives you an edge. So edges can arise in an image because of a variety of factors. Okay. Now, just to show you where there are edges in an image, so I took a line here. This line is passing through an image, right? And let's just look at the color values, the gray level values of this line. So this part is a bit bright, it's like white, so these are higher values, and then there is a sharp drop here inside the store because that's dark, so that's that sharp drop. And then you still have passing through white, but then you cross a pole, so that's like another sharp drop. Okay. And then you have these white lines, and then this dark region which is corresponding to this door, and then another dark region which corresponds to this part, and so on. Okay, so this is what the color profile of this line looks like. Okay, and so what are edges really? Edges are sharp changes in this intensity profile, right? It's a discontinuity or a sharp change in this intensity profile. Okay, now edges are uh, edges are important in human perception also. So this is a very interesting experiment. I find it interesting. This was done at UC Berkeley by Jitendra Malik's group. What they did was there were a bunch of people working on edge detection. So and there was a time in computer vision when there was a race to find the ideal edge detector, because people thought that if we find a very good edge detector, uh, we we will we will solve some vision problems really well. Um, that view is no longer a dominant view now, but it was there. So what these guys did was they said, well, what is a good edge detector? So a good edge detector should have the performance of a human person. If a human says there's an edge here, my edge detector should also say that there's an edge here in the image. Okay, so that's like the gold standard maybe of the quality of your detector. So what they did was they gave a lot of images to graduate students. Grad students don't have any rights. They're like slave labor. So so they gave them a lot of images, and they said mark edges on each of these images by hand. Okay, so complicated images like this one and this one and so on, and they gave each image to multiple people to try to see whether their understanding of an edge is consistent with each other. Okay, so these students went and they marked all those images and so on, and then they found out that yes, their understanding. So what is shown here is the results of all those students combined into one view. The darker the edge is means that edge got more votes from more human observers. Okay, so the lighter one, somebody. So for example, this edge here, the middle one here, well, somebody marked this and somebody didn't mark this, because I mean, a lot of people thought that's not important because that's like an internal edge of this mountain. The important is this top one. So the top one everybody marked, so that's coming out to be dark. But these internal ones, somebody marked, somebody did not mark. Okay, and so what they showed from this study is that that there is no actually ideal edge detector if you talk about human perception of edges, because people will disagree on where there are edges. I mean, what portion of an image is an edge or not. Okay, however, they also showed that while people do disagree, there is a hierarchy to that disagreement. There are some edges that everybody agrees on because they are more salient in the image, and then there are some that people differ on because they are less salient in an image. So if you organize them by importance, there are some on which there is no doubt that there are edges, right? And then there are rest which are kind of doubtful. Okay, so they are hierarchically consistent in a way. Yeah.
The objective is to find the object, and the object will be quite visible in the photos. Everyone will mark it. Other details might not be important if they find track the object.
So you're saying the objective is to find the object, but yeah, in this image, where is the object?
The cat.
The cat is the object, but the tree is also an object, and the branches of the tree could also be an object. It depends on what you define as the object. So it's not that straightforward, right? Okay, so one of the fundamental operations in image processing that we do, and we do that. I'm introducing that as an operation to find edges, but really I could do a whole lot of different things with this operation. And in fact, we will see this operation again when we come to deep learning, because it's also a very fundamental operation in deep learning networks, in neural networks now, is the convolution operation. Okay, so it's actually a very, very important operation for you to understand. So those people who have taken signals and systems type of class, how many people have done that? Yeah. So those people who have seen a signal and systems class have already seen this. Except typically you treat that as one-dimensional convolution in signal and systems, and here we are going to treat that as two-dimensional. But even if you have not seen this before, that's okay. It's actually a simple operation, and I'll describe this in an intuitive way, not a mathematical way. Okay. So the convolution operation is the operation of applying a mask to an image. Okay. So you have an image, and then you have some mask. A mask is a small kind of set of weights in a grid. Okay. So a mask is a set of pixel positions and weights, and it has an origin. Okay. So it's a set of weights at different positions, and they have weights. And I'm gonna learn how to apply a mask to an image. Okay. So this could be a mask. It's a mask of all weights 1 arranged in a 3 by 3 grid, and the mask has to have an origin, so the origin here is the center pixel. Uh, you, the term mask in Photoshop is used in different ways, but this type of convolution masks are also available in Photoshop. You have a bunch of them already available coded, and you have even an option to define a custom mask in Photoshop. Okay, but the term mask is used in different ways in Photoshop to hide a portion of the image, for example. That's not what I'm talking about. Okay, so if you have taken a signal and system class, this is really the impulse response of the LTI system. But I'm going to not introduce the flip, so it's the flipped version of the impulse response. Okay, it's minus h of t. No, sorry, h of minus t. Okay, the rest of the people can ignore this comment. It's not important. Yeah. A mask is just this. It's a grid with some weights in it, and it has an origin. That's it. Sorry? This whole blue thing is a mask. It's a set of 3 by 3 pixels with some weight in them.
So ये mask introduce pixel
Sorry?
ये basically हम image में pixels में apply करेंगे.
Yes. I'll show you how to apply it. I'm just telling you what's a mask right now. Right? No, it could be different. This is also a mask. This doesn't have equal values. The value in the center is higher than the values around it. This is also a mask. It's a valid mask. It's not square. It could be really any shape. Weights. No, they are weights. I'm coming to that, right? So I've just defined that there is a mask which has weights in it, and it has an origin. Even the origin doesn't have to be in the center; it could be somewhere else, but typically it's in the middle of the mask. Okay. Now the operation of convolution is the operation of applying a mask to an image. Okay. So how do I do that? Let's say this is my image. So these are pixel values now. And we are only going to talk about gray level images. We are not going to talk about color images, even though color images are just 3 layers of gray level images in a sense. But we are not going to talk about color images for now at all. Okay. So these are some pixel values in an image. Half of the image is pixel value 40, and half the image is pixel value 80. The higher the value, the more brighter that portion is. And pure white is 255, and pure black is 0. Okay. So you can imagine what this image looks like. It looks like a box where half of it is darker and half of it is a bit lighter. Okay. Now I have a mask which is this. The origin is at the center, and this mask is 1 by 9, 1 by 9, 1 by 9 all over. I wrote it as 1 by 9 times 1s. If you were writing it in MATLAB, you would say 1 by 9 times 1s 3. Okay. All right, so I want to show you how I will apply this mask to the image. So what you do is really you slide the mask all over and apply it at every pixel location. Okay, so let's say I want to apply it at this particular location shown by the blue square. Okay, so what will I do? I align the center of the mask here, where I want the result to be, where I want to compute the result. I align the center of the mask here. So that's really how the mask would overlap, right? And then what I do is I just do point by point multiplication. So whatever is the weight multiplied by the pixel value. So I do 1 by 9 times 40, 1 by 9 times 40, 1 by 9 times 80, 1 by 9 times 40, 1 by 9 times 40, 1 by 9 times 80, and so on, right? I do that, and then I sum that all up. And that's my result for this location. So it's really weight to pixel value multiplication for all of them, and then add that up. Okay? Yes. We'll come to neural networks. No, not really. I mean, neural networks don't have to work like this, but one of the very popular techniques in neural networks now in deep learning, which is called convolutional neural networks, CNNs, um, are actually implementing some sort of convolution. Essentially, I mean, we'll come to that in full detail. I'll describe inshallah in complete detail what a convolutional network is. But essentially, if you want a preview of the answer to that, essentially what the whole neural network is doing is learning a particular mask or a particular set of masks actually, okay, to achieve a certain objective. So that's what these CNNs do. Yeah. एक वैल्यू मिलेगी या वो मिडल वाली जब मैं आउटपुट क्रिएट कर रहा हूँ तो मिडल वाली में रखते हैं.
सर ये जो इनिशियल वैल्यूज लेनी है वेट्स लेनी है ये रिटर्न होगी कि
No, you define the mask. I'm just telling you, given a mask, how to apply on the image. You define the mask. Yeah.
some mask is apply करते हैं
We'll come to that, inshallah. Why do we apply them? Yeah. We apply it, if I want a value at whatever pixel, I apply it there. So I've applied it to one pixel, I have to really apply it to all of them. Right. Okay, so what will be the result here? There are 6 of these 1 by 9 times 40 terms. There are 3 of these 1 by 9 times 80 terms. So I sum them up, I get 53. Which is kind of a weighted average of these things, right? In the weights of 1 by 9. So it's kind of like in the middle of 40 and 80, it's somewhere in the middle, right? So what's the effect of this mask? Well, by the way, I applied this all over. I'm assuming that there are 40s going this way and there are 80s going that way, right? So even if the mask kind of spills over, there was an 80 there. I'll come to this in just a moment. So what I got was, when I'm over a region which is all 40s, it's 1 by 9 times 40, 9 times, so that's just a 40. Okay. But when I'm in a region where there are 2 columns of 40, 1 column of 80, so I get 53. And when I'm in a region where there are 2 columns of 80, 1 column of 40, I get 67. And then when I'm in a region over all of 80s, it's 1 by 9 times those 80s, 9 times, so that's just 80. Okay. So if I apply it everywhere, all over, this is what I'll get.
So अगर हम लोग अपने किसी कॉर्नर पिक्सल को अप्लाई करें तो उसके जो बाकी जो बाहर चल जाएंगे सब वो जीरो समझ
That's a good question. Let me just come to that in a moment. Because I'm giving you a small example, this question is important. But in very large images, it's actually like, I mean, the image is like 1,000 by 1,000 pixels. This is an issue only for the last column, so it's not that significant an issue. Okay, but I'll address this in a moment. So my question is, what's the overall effect of this mask when I apply this mask to the image? By the way, one thing here, when you are applying it pixel by pixel, while you apply it here, this pixel value changes. It's not that when you apply it here, you will use the change value. No, the output is being written in a separate grid, right? So the input values don't change as you are applying the mask. So it's not that the mask will overlap with the last change value and so it will generate something else. That's not the idea. Okay. What's the overall effect of this mask?
तो आपके जो पूरे कलर वाइट और ब्लैक में थे वो आपको basically आपका एक shade आपका change होगा.
Yeah, so really this is a smoothing filter. There was a sharp transition in the image, and that has been smoothed out now over a larger area. Okay, here I've shown you that in color. So this was the original image, and this is the kind of smoothed version to that. So that sharp transition that I had in the image has been spilled over a larger area now. Okay, yeah. Yeah, you can do this with color images. There are several ways to do that. One way is, the simpler way is that you just apply the same smoothing filter to R, G, and B separately and then compose the image. But you can even have three-dimensional masks. If you want a relationship to change between R and G and R and B, you want the colors actually to change, then you can even have three-dimensional masks. Yeah.
Sir, जो मुझे smooth ना लगे तो मुझे ज़्यादा better कोई नजर नहीं आती सारी combination वाला
We are not talking about what we are going to do with this. I'm just telling this is a smoothing filter. If you wanted to do smoothing, this is a smoothing filter. Okay, we'll come to all these questions. I mean, I'm just getting started. Okay, so this is an image. If I apply the smoothing filter all over this image, this is what I get. Notice what the filter is doing. It's just taking average of the nearby pixels. So when I take average, things get blurred. Look at the fine details of the hair here. They are like smudged over here, because the filter was like averaging out neighboring pixels. Okay, so the details are a little bit blurred, right? In fact, if I took a really large smoothing filter, I mean an average mask, but which has a much larger area, I can get a lot of blurring. That's a good point. I could either take a large average filter, or I could take a small filter and apply it multiple times. Both are not exactly the same thing, but they're close to being exactly the same thing. It's the same mask. I applied it all over the image. I'm just showing you the effect in visually rather than in numbers, but it's exactly the same thing. Is that clear? Okay. So your question, what about corner pixels? Well, I could do a lot of different things. I could, because the mask will spill over outside the image on the corner pixels. I could either expand them with virtual pixels and fill them with 0, or fill them with the nearest pixel value, like 80 in that case. So I could just expand that out, or I could just ignore them. Do whatever. It doesn't really matter, because masks are typically small in size, images are typically very large. So half a mask spilling over is only like a thin edge in the image. Whichever way you treat it, it doesn't really matter. I think the most common way to treat that is to assume that the spilled over part of the mask is just being multiplying with zeros. So really you can ignore that. Okay. Now for just a comment for those who have taken signal processing, because in convolution you have a flip and a slide operation, and I introduced masks. Most of my masks are symmetric, but even if they were not symmetric, I introduced masks as a direct operation. So really, it's the flipped version of the impulse response of the system. Okay, of the LTI system. That's all. Otherwise, it's the same convolution that you study mathematically, except it's two-dimensional. So it's really two-dimensional convolution. Okay. Yeah. Okay, the question is, why can't we consider that correlation? If the mask was actually an image content, it wasn't like just weight values, then that would be the correlation between those two images. Yeah. It is correlation, yeah. In fact, in correlation, you don't have the flips, so you could think of it as correlation. Okay. Except you are correlating. Typically, you correlate values that you expect to match. Here, you have ones, and so I wouldn't I wouldn't call it correlation, even though technically I could, between like highly diverse signals, but I wouldn't call it correlation. In fact, I'm calling it convolution. It is exactly convolution, and the purpose I'm achieving from that is also what typically we do with convolution. I'm just I'm just explaining to you guys that to be mathematically correct, it really should have been a flipped version, if I want to call it the impulse response of the system. I didn't do that just to not add complexity, because those who have not studied LTI system will say, why are you flipping it? Yeah, the rest of people can ignore all of this. It's not relevant. Okay, so now, given that I've introduced to you what a mask is and how do I apply that to an image, the question is, how can I do edge detection? Okay, and in its simplest form, the objective of edge detection is that given an input image like this on the left hand side, I want to find an output image which has like 0 values or low values everywhere there isn't an edge, and it has high values where there is an edge. Okay, so how can I do this problem? Any ideas? That's actually very correct. So edges are edges are really locations of high intensity variation, right? I could say I'm going to do it a bit more formally, even though what you said is exactly correct, but I will derive it a bit more formally. So edges are locations where intensity variation is high. Everybody agrees with that? Another way to say the same thing is that the rate of change of intensity is high. Intensity is changing rapidly. So the rate of change of intensity is high. Which means what? What is the rate of change of something? It's the derivative of that, right? So how do we find the rate of change of intensity? Well, we can do that by differentiation. That's what differentiation gives you. That's what calculus is all about, right? It's about rate of change. So in its continuous form, the rate of change of something, the derivative of something is written like this. F prime of x, which is the derivative of x, is df over dx, which is limit delta x, a small step in x tends to 0, fx minus x minus delta x, fx minus delta x divided by delta x. Okay, I want you to understand this. What's the notion of derivative? So if I'm standing on a function and I want to find the derivative of that, what I should essentially do, what this equation is saying, what derivative really is, that I should take a step, let's say to the right, okay, and see how much is the change in the value of the function. Okay, and that change, so let's say I'm standing at function, where I'm standing, the function value is 10. I take a step and then the function value becomes 8. So the derivative would really be 2 minus 2 really, except my step size has to be very small. Then it's a derivative, right? It's how much the function changes if you make a small change in your location. If you make a small change around your position on the x-axis, how much is the function going to change? That's your derivative, right? And this is what this equation is saying. It's fx minus f of x minus delta x, which is a small step. So the difference between them divided by the step size, and the step size should really be infinitesimally small for that to be a derivative. Okay, so if you are on a mountain, the derivative is really, if you take a step, how much will you fall? That's the derivative, but take a really small step. Okay, so in its discrete form, if we have pixels in images, we don't have a continuous function. So in its discrete form, what I can do is I can choose the smallest step size and just reevaluate this equation. And the smallest step size between 2 pixels is really, if I'm taking integer pixel location, it's really 1. So I can just substitute delta x is equal to 1, and that means the denominator becomes 1, and then the derivative is really fx minus 1, which is exactly what you said. You said if I want to find an edge I'm looking for intensity variation, so I should just subtract that pixel from its neighboring pixel. And if that number is high, there is an edge there. If that number is low, there isn't an edge there. Okay. So this is the notion of discrete derivatives. I'm talking about one row of an image because I did only derivative in the x direction. So this is the row of the image that I showed you earlier, 40s and 60s. If I just do, I subtract this from this, I get a 0. I subtract this from this, I get a 0. I subtract this from this and get a 0. Okay, but when I'm here, I subtract this from this, I get a 40. Okay, and then all the others are 0. So notice that the edge gets highlighted because that's where the variation was. Okay. In fact, if I want to implement this as a convolution operation, this could be my mask, right? Because that's what convolution does. It will subtract wherever this mask is, it will subtract, it will multiply this by +1, it will multiply this by -1. So it will be really a subtraction of these two pixels. So this mask with this origin, now this is a non-symmetric mask, so in LTI systems, think about it like flip, but that's the convolution. And we write it as the convolution of fx, which is the original signal, convolved with, I'm using this symbol for convolution, convolved with gx, which is this symbol, which is this function. Okay. If I want, I can find the double derivative of fx with respect to x, because the double derivative is nothing but the derivative applied to the first derivative, which means I apply this mask once again to this signal, and I'll get a 40 and a -40 here, and that would be the double derivative. Okay. Any questions? Yeah. No, we don't. I said ignore the end pixels. We are not talking about circular convolution here. We don't really need to. Yeah. Yeah, that depends on how you define your origin. Yeah, really. Okay, so what does that do really? I mean, what does this operation do really to images? This is an image, okay, of an environment. So if I apply this now, because the x direction is going vertically down, so I have a +-1 mask applied here. I applied that to all images, to the whole image. Now I'll get some positive values in the image, I'll get some negative values in the image, right? When I do that, because there's a -1 there and +1 there, so there will be some positive numbers and negative numbers when I apply this mask. So what I did was I just scaled them between 0 and 255. So really 0 is roughly in their middle, so that became a gray. Okay, and then the white ones are positive edges, I mean, which was a change from a high number to a small number, and the dark ones, which are below 0, are the change from a small number to a high number. Okay, because I could get a +40, a ±40, I could get all sorts of numbers. Okay, so now notice what's happening. All the plane regions of the image, let me show you the image, right? So all the plane smooth regions of the image have like low values close to 0. But wherever you have an edge, you have like high values, either positive or high values which are negative, like these black ones. Okay. I could apply them. I did this in the x direction, the mask in the x direction. I could do that in the y direction. And then that will highlight changes as I move along the y direction. Now, as I move along the y direction, these edges, which are actually going in the x direction, get highlighted, because that's where I see the difference. It's interesting to contrast this with the previous one, right? Here, I was applying the mask in the vertical direction, in the x direction. Most of the edges that I find are like horizontal. I don't find these edges because the mask was vertical. But in this one, I highlight the vertical edges because the mask was horizontal. So I found a change as I move in the horizontal direction. Okay. So this is really the x derivative of the image, the discrete derivative in the x direction of the image. And this is really the discrete derivative in the y direction of the image. All right. Okay, so good question. How do I find the derivative in both directions together, or how do I combine that into one image? So you guys have studied calculus. So have you done like multivariate calculus, calculus of more than one variable? So what you are asking is exactly that. How do I find the derivative of a multivariate function? Because I have a multivariate function here. I have a function of x and y. The image is a function of x and y. So it's a multivariate function. So how do I find the derivative, the gradient of a multivariate function? I do partial derivatives. So this image really is partial derivative of the image in the x direction, and this is really partial derivative in the y direction. Okay, and there is no like one derivative which is a derivative in both the x and y directions, because that's not how a derivative is defined. To define a derivative, you have to, because you have a step, you have to have a direction of that step, right? So that's why derivatives are directional entities. Okay. All right, we'll stop here, and inshallah continue next time. I've introduced what's the notion of a derivative and of an image derivative, and we'll see how we can use them. Yes, there is a question. Yeah, I'll kind of discuss that in the next lecture, inshallah. Okay, if by the end of next lecture you don't find a satisfactory answer to that, you can ask that again.